Okay, so this problem deals with an apparatus that's used to measure thermal conductivity of a material. And I like this problem because it illustrates some important things about Fourier's law. How do you measure thermal conductivity of a material? One way would be to impose some known heat flux or heat flow and then measure the temperature distribution or the temperature gradient inside the material. And from there, with Fourier's law, then one could solve for the thermal conductivity. That's the basic idea. But in practice, there's some things that you have to think about. One is that you want to make sure that heat flow is only going in one direction. If you have heat flow, for example, here coming out the sides, then it doesn't reduce to a one-dimensional problem, and you have to consider some more complications to your analysis. So this is formulated in such a way that there's insulation around the sidewalls. That is done to help make sure that the heat flow is going only up and down, in the up and down direction. The other thing is how the heating is taking place. If you just had one of these samples here and you were heating it from the bottom, then there would be a lot of heat input coming in that you wanted to go in one direction, up and down, vertically here. But then you would really have to insulate it very carefully at the bottom because you don't want any heat loss coming out. And that would be maybe more difficult to do because that's really the source where most of your heat is, and you want it only to be directed upward into the sample. So to address that problem in this design, there's two samples that are stacked end to end. These are rod-like samples, rod-like bars of a material, and they're put end to end like this. And they're heated from the center. So what this does is when the heat flow is applied in the center, then most of it is now going to be directed into the materials, either upward or downward. There's going to be less room for heat loss through the sides because that could only happen through this thin region that's exposed to the sidewall. This design then ensures that most of the heat energy is directed into the samples. And so that's another reason to adopt this design.